So that means now what I am interested in is now to find out. So we have already figured out now what pressure is. We understand a lot about pressure. We still do not know enough about velocity, and we can figure that out if we integrate this equation, because this is is this now a partial differential equation or a ordinary differential equation? It's an ODE. You know how to solve it. You can go ahead and solve it. So it's a second derivative, and because this is a constant, I can simply integrate it as du by dy is equal to 1 by mu times dp by dx plus times y plus a constant c1, and u is equal to 1 by mu dp by dx into y square by 2 plus c1y plus c2, right. So that's what my velocity field is going to be, and c1 and c2 will be the constants that are coming out of integration, and you have to find that out from the boundary conditions, okay. And you know what those boundary conditions are, right? We already wrote it down. We had written it down as somewhere there, u at walls, right. So that means walls is either at y is equal to 0 and let us say some y is equal to h, where h will be the width of the channel now. So let us define all those things. So that is my okay, let us make another picture. So that was my original wall, that is what I called as x, this is what I am calling as y, let us say that is equal to h. So this wall is y is equal to 0, this is y is equal to h, and when y is equal to 0, you know u is equal to 0, at y is equal to h also, that is going to be 0. Now let us do a slightly different problem, because that will do two things in one go. So what I am going to do now is that the same problem. So what we have done really is that you have applied a pressure gradient. In other words, you have applied a large pressure here. For example, you will put a pump. Okay, you put a pump that will exert a large pressure here, which will move the fluid in the channel, right. So along with that, let us say that you are not only applying a pressure gradient, you are also going to move this upper plate. So this upper plate is going to go with a velocity capital U. What would that do? That can also drive the fluid, right, because you take fluid between two plates, you are moving one of the plate, the fluid will automatically move. So that basically what I am trying to say is that there are two ways of moving fluids typically. One is that you put a pump, in other words you apply a pressure gradient which can generate a flow, or you move one of the boundaries, okay, like this, and then it will also drive a flow. Okay. So we are looking at a situation now where you have applied a pressure gradient as well as you are moving a boundary. Okay, and then let us calculate what is the velocity profile and see how different those velocity profiles are going to be. Is that clear? So I am changing the gear a little bit now. So that is the situation. So we know that so far, so till writing down that equation, we only cared about the so we did not really impose the boundary condition. Only thing that I am doing is by imposing u is equal to capital U at y is equal to h, I have just changed the boundary condition. So this equation whatever we have derived so far should remain so, right. Is that clear? Okay, so I am going to use that and apply these boundary conditions. Can you calculate C1 and C2 now? So you have a fluid which is driven by a pressure gradient, okay, whose velocity profile is going to be this, but it is also that fluid is in between the plates and one of the plate is moving with a certain velocity capital U. So the fact that at y is equal to 0, u is equal to 0 implies C2 equal to 0, and then the only non-trivial boundary condition is that y is equal to h, u is equal to capital U. So, I can say that capital U is equal to 1 by mu dp by dx h square by 2 plus C1 h, and that gives me C1 is equal to u by h minus 1 by mu dp by dx h square by 2, which means now I can substitute. What is that? What mistake did I do? Oh, there is an h here, so this is gone. Okay, correct. So, that means my u is going to be 1 by mu dp by dx y square by 2 plus u by h minus 1 by mu dp by dx h square by 2 times y, and that is equal to 1 by mu dp by dx. Oh, I again made the mistake, this is h, dp by dx into y square by 2 minus h y by 2 plus u y divided by h. Is this correct? Okay. So, that is the velocity profile in this case. So, dp by dx, will it be greater than 0 or less than 0? Yeah. So, you can so if you want to recognize the fact that dp by dx is less than 0 and write down this quantity as minus dp by dx, this term will reverse, okay, and that is typically the way you would write it. Let us see different cases now. Case 1, dp by dx is equal to 0. If dp by dx equal to 0 means you have not applied any pressure gradient, only the top plate is moving, what velocity profile would you get? Oops. So, you find that u is equal to u y divided by h. Okay. So, that means I have a plate, this was my y is equal to 0 and this was my y is equal to h. At y is equal to 0, u is equal to 0 here. This plate is moving with a capital velocity u. So, at y is equal to capital H, u is indeed equal to capital U. So, it has some finite velocity and the variation is linear. So, that means my velocity profile is going to look like that, right, and that is something that you have already seen probably, and this flow is known as one of the simplest flow fields that you can get. Okay. And this is very important in terms of determining viscosity and so on, this particular flow field, and you will see that probably next week and week after, how do we utilize this further. So, case 2, u equal to 0. So, that means and dp by dx is not equal to 0. So, that it means you have imposed a pressure gradient, but you are keeping the wall velocity 0. So, it is two stationary plates, you have fluid in between and you have imposed a pressure gradient. So, what does u come out as? So, that goes away, it just remains that. So, let us write it as 1 by 2 mu times minus dP by dx times hy minus y square. Is that correct? Yeah. So, you have plate, y is equal to 0, y is equal to h, you have applied a pressure gradient dP by dx is less than 0. Okay. So, because pressure will be larger, pressure here smaller pressure, and fluid is flowing from larger pressure to smaller pressure, and the flow profile is going to look like this. At y is equal to 0, u is 0, at y is equal to h, u is again going to be 0, somewhere in between it is going to be a maximum, and that maximum can only be at the center then. So, it will look like that, okay, a parabolic velocity profile. So, this flow is known as plane Poisson flow. Okay. Yeah, doubts? Ah.
Suppose we don't make the pressure difference because of a pump or something, due to the velocity, fluid flow itself, can there be a pressure difference generated?
So, it is the same thing. So, if you have a, so in this case what you are asking is that you have generated a flow field, in which case there can already be a pressure difference. Okay. So, it is a, so because, so if you look at this equation, we ended up saying so that one. Okay. It says that a pressure gradient generates a fluid flow, that is what I interpreted it as, or you could say that yes, there is a flow that will generate a pressure gradient, and the way we typically do it is we apply a force and get a motion. We do not say that we actually get a motion and because of that, that force existed, which is an equivalent description, but it is probably less physical than interpreting it the other way. Okay. So, flow will be typically associated with a pressure variation, or a pressure variation would generate a flow. And yeah.
So, why do we neglect the gravity in the biomomentum equation?
You could. So, right now I am looking at a pipe that is actually perpendicular to the gravity. Okay. So, the only thing that would have happened is that there can be hydrostatic pressure that is perpendicular to this. Okay. So, in reality that would mean that when we said this quantity, right, dP by dy is really rho g, if you wanted to include that. So, the pressure will split into two parts. Pressure will have a hydrostatic part which will balance the gravity force, and then there is a pressure variation in the x direction which is going to balance the viscous forces. Does that make sense? Because hydrostatic pressure will not generate a flow. So, it is just that just that fact, that is why we do not care about gravity at all. Gravity is in the y direction. So the, yeah. You can, and what that will give you is that pressure will just come out to be rho g y, which will have nothing to do with what we do next. Okay, P is only a function of y. We did not care because I am saying that, so this pressure really can be interpreted as the total pressure minus the hydrostatic pressure.
But sir, in this case we can't say that P is a function of x only.
P is, but we know everything about what is it in y. P is just, so see the y, so we have a uniform channel. So, okay, so therefore, any point that you take, if pressure is varying, that is just according to this. What is interesting for us is what is happening in that direction, which is what we did not know, which is what we calculated. So, now you could, if you like, you could expand by saying that okay, I am going to add my rho gx term here, I will add my rho gy term here, which would give me dp by dy is equal to rho gy, where I am only talking now my gx is 0, I only have gy, which gives me p is equal to rho gy. Okay.
I'm saying that it won't be constant then, because the pressure is function of y also, then there will like mu d square u by dy square is function of y.
So, that is what I am saying, that the pressure has two components now, one is due to gravity, the other is due to flow. What we have calculated is the pressure due to the flow, not due to gravity. Okay. So, in some, so this pressure, so let us do it this way, let us say that this is some, I think this is called a dynamic pressure, that means we have already removed the hydrostatic part from it. So, we will call it a PD, then it is okay, and that is because gravity will not do anything. But if you were looking at a pipe which is perpendicular to gravity, then you should have been careful, because these two components will add up in the same direction now. Okay. So, we will see how to, so see that is exactly what you do it in Bernoulli's equation. You have a pressure head, you have a velocity head, you can have a gravity head, right. If you talk about a pipe in a, in a horizontal direction, then there is nothing gravity will do. Okay. Gravity will not generate any velocity, but if it was in the perpendicular direction or in the direction that is parallel to gravity, then gravity could induce a flow, and which we will see how we will write down gravity included in terms of pressure field and so on at a later point. So, at the moment let us just say that either we have a situation in which our flow is perpendicular to gravity, and therefore, the hydrostatic pressure is not going to do anything. Anything else? Okay. Oh, I need to do two more cases. So, the next case, can you draw now case u is not equal to 0, dp by dx is less than 0, and case 4, u not equal to 0, dp by dx greater than 0. You can plot and then come back next class.